Sorry we got cut off, but we're almost done. I had just said in that previous video that this is called the mole bridge. It bridges the data or the numbers from the starting material and the product. So it's a way to get from the starting material and make sure that you end up at the very end with your product on top. In this case, in grams. Let's do the same thing for starting material number 2. We got moles of 2, and then we're going to cross over the mole bridge. Same thing. You get 1 mole of product for every 1 mole of 2 that you use. And we're just getting that from the idea that that ring is this ring, and that ring is that ring. Okay, that's safe to say. So we need 1 of these, 1 each, to make 1 product molecule. That's where we get the ratio here. And then one more time, we have moles of product now, I think. Get rid of moles, get rid of 2. We have moles of product, but we really want grams of product. 268.31 grams divided by 1 mole equals, I like to do this in parts, 0.726 divided by 140.57 equals times 1 times 268.31. Okay, we have 1.3, round up to 1.39 grams of product if 2 is the limiting reagent. So based on these two numbers, when we run the reaction with this amount of 1 and this amount of 2, when we get up to 0.817 grams of product, we have round out of 1, and we can no longer react it with 2. So we stop here. This is your limiting amount, or this is the amount of product, because 1 is the limiting reagent. Now there are 2 things you want to do with this information. Before you forget, right, put that theoretical yield here. And I already forgot. 0.817. Okay, don't forget that. And also, I want to make the limiting reagent equal to 1 equivalent. So the limiting reagent in our case is compound 1. So for compound 1, I'm going to put 1.00. Now the equivalent is just the mole ratio. So we are solving for x. Okay. Oh. Well, we don't have to, but I'll put here EQ for equivalence. And what do we do here? Do you remember how you cross multiply and then divide it by this number? Because I want to solve for x. Literally, the math is this. I'll solve for x. And so we have 0.00516 times 1 divided by 0.00305, and I get a number, put 3 significant figures, 1.69 equivalents. What that means is, for every 1 part of 1, I'm using 1.7 parts of 2. Now, this is not grams, right? This is the molar ratio, not the gram ratio. And so if we want to scale up, right, if we want to make 10 times as much, then we could multiply this by 10, this by 10, multiply this by 10, this by 10, and get our new amounts. It's just a kind of a convenient way to quickly see how much excess we have, okay, and how to scale up. Now, the question is, that some of you might have is, well, I thought this was a 1-to-1 ratio. Yes, according to the equation it is, but in practice, many times you want one of them to be in excess because that excess material is easier to purify out. and we want to make sure we get as high yield as possible by ensuring that we have enough reagent to use up one of the other reagents. So in this case, I definitely have enough 2 to use up all of this. And then according to this, that excess 0.69 parts, I'm hoping that I could purify it. I could remove that residual excess. And typically when you design a reaction or design a synthesis, you want slight excess of one of the reagents to ensure that you use up the other one. Okay, we're not quite done. We found out the theoretical yield, which was 0.817 grams. The theoretical mole, because this is the limiting reagent, would be the same as this amount, 0.0305. Now, this is all theoretical, right? If the reaction works perfectly, theoretical yield in moles, this is theoretical yield in grams, and the equivalence, you don't have to write the equivalence here, but technically it's 1. For every 1 of this, we get 1 of the product. But it's not really that practical, or it's not really an important piece of information to know the equivalence of the product. The equivalence between these two is what's important to know. So go ahead and fill in your theoretical amount in grams and the theoretical amount in moles, and that should be fine. Alright, so that is the pre-lab. You're still going to fill in all the other parts that you know need to be filled out, like the step-by-step procedure. Please put it in the correct location. The materials table is after the source of procedure, and you have 2 parts to the materials table, right? The characterization that you'll do in lab. Okay, so before you leave lab, make sure this is filled out. And this one is filled out before lab, where you Google the hazards for each of these chemicals that you're using. If you have any questions, you could definitely email me. I think that's it. Let me just double check that we have everything. Again, you don't need to show the math, okay, but I would put it in your notebook on the left side of the notebook, just in case you need to refer back to it. Okay, let's say you have a different number than your lab partner. You could always go back to see how you calculated those numbers. All right, good luck preparing, and good luck when you do your first synthesis, for your first reaction for Organic Chemistry 1.